Next speaker is Aiko Yamaguchi from NEC Labs, who will be speaking about engineering challenges in quantum annealing using Kerr-parametric oscillators.
Thank you. Good afternoon. First of all, I'd like to say that it is a good pleasure and honor to be invited to speak here today. Thank you very much for inviting me here. My name is Aiko Yamaguchi. Today I'm going to talk about engineering challenges toward our quantum annealing machine. Okay. Before I start my talk, let me introduce myself. I got a PhD in 2019, and at that time, I studied cold atomic magnetometer to search for fundamental symmetry violation, especially time reversal symmetry violation. So my background is experimental physics. And after I finished my PhD, I joined NEC and started to work on the project of quantum annealing machine based on a Kerr-parametric oscillator. And since 2019 October, I'm concurrently working at AIST. And my research interest is a quantum annealing machine and superconducting quantum circuit, especially Josephson parametric oscillator. Next, let me introduce NEC's initiatives in the field of quantum computing. In NEC, we aim to contribute to solving social issues based on annealing technologies. We are accelerating the activities including collaboration with D-Wave and offering simulated annealing method using our original vector engine called SX or Tsubasa. And as for research and development, we are leading the development of quantum annealing machine using superconducting parametron. And in this presentation, I will discuss the recent progress of this project. At the same time, we are working on the development. Developing a gate-based quantum computer. Before I start talking about annealing machine, I'd like to introduce you this project shortly. In Japan, a national project called Moonshot project is running. This project targets to realize a fault-tolerant quantum computer. In this project, various hardware categories are being developed in parallel, and superconducting system is one of them. And the project manager of superconducting quantum circuit group is Tsuyoshi Yamamoto from NEC Corporation. In order to realize a fault-tolerant quantum computer using superconducting qubits, various technologies developments are needed. So you can easily imagine high-quality qubits for low error rate is important. And it is important to decrease the number of qubits, which decrease the number of qubits. And on the other hand, the number of qubits that can be controlled is limited due to various restrictions. So efforts to increase the number of controllable qubits is also important. In this project, wide range of technologies are being developed in collaboration with several teams. I listed all collaborators here. 6 private companies, 8 universities, and 4 national institutes are included. This is the project on quantum gate method machine. And introduction has been a little bit longer, but now I start to focus on the development of the project of quantum annealing machine. We are developing a quantum annealing machine in the framework of this NEDO quantum and Ising computation project. In this project as well, multiple research institutes are working on ranging from quantum processor to the software platform. The project manager is Kawabata-san, who gave a talk about another quantum annealing machine yesterday. And in this project, this project targets to realize a quantum annealing machine using parametron and also NEC computer. And this quantum annealing machine is the main topic of my talk. This machine is based on quantum parametron, and quantum parametron is also called as a Kerr-parametric oscillator. As you know well, one of the biggest challenges in realizing a quantum annealing machine is how to realize O2O connectivity. But it is not easy to prepare a variable connection between the spins that are located far away. And one of the methods is the LHD scheme proposed by Lechner, Hawk, and Zoller. In this method, the product of two Ising spins is represented by one physical spin. The number of spins increases from n to n times n minus 1 over 2, but it allows us all represent O2O connectivity. The original coupling between spins becomes the local magnetic field for the physical spin. By tuning this local magnetic field, we can tune the interaction between the Ising spins. Because of the increased number of spins, new constraints will be required. For example, looking at these four spins. These four spins represent the product of 1, 3, 1, 4, 2, 4, and 2, 3 respectively. If the original spin value is minus 1 or plus 1, the product of these four spins must be plus 1. This constraint is necessary for all other spins. In other words, from a perspective of device development, it is necessary to realize four-body interaction. A proposal has been made to achieve the four-body interaction using Kerr-parametric oscillator, KPO. And KPO can be realized by Josephson parametric oscillator, JPO. So next, I will explain about JPO and KPO. This picture exemplifies the device. The JPO structure is an LC resonator in which the squid contributes to the inductance. The squid consists of two Josephson junctions, and Josephson junction has Kerr nonlinearity. So this results in the Kerr nonlinearity of the JPO. The squid loop is inductively coupled to the pump line.
Would you like a laser pointer? Is that easier for you?
Yes. Thank you.
Sorry. Thank you.
Thank you. The inductance of squid can be changed by the magnetic flux which penetrates the squid loop. This results in the frequency tunability of the JPO. The parametric process is often compared with a swing. For swing, bending and stretching cycles correspond to the parametric drive. And in case of JPO, it is equivalent to applying a magnetic field with the frequency about twice the resonance frequency of JPO. When this power exceeds a certain threshold, JPO begins to oscillate spontaneously. This is a parametric oscillation. As a characteristic of parametric oscillation, there are only two oscillation phases. And when it's freely oscillating, the two states occur with an equal probability. A JPO is originally a classical device. However, if the Kerr coefficient is larger than photon loss rate, it can act as a quantum device. And we call it Kerr-parametric oscillator. This condition is so-called one-photon Kerr regime. I mentioned that the oscillation phases is limited to values, and each state corresponds to the coherent state. And in case of KPO, the superposition state of these two coherent states, or Schrödinger's cat state, can be generated. Coherent state is an eigenstate of annihilation operator, and it's tolerant to photon loss. Here, I show the Hamiltonian of 4 JPOs connected with single Josephson junction. In quantum annealing procedure, initial state is vacuum state, where neither parametric drive nor coherent drive is applied. When the amplitude of both signals increases, the state of KPO bifurcates to the coherent state, alpha or minus alpha. The two coherent states correspond to spin up and spin down. Here, I explain the measurement setup of our quantum annealing machine. This is a microscopic image of JPO, KPO. Yellow part is niobium, and dark part is the surface of silicon substrate. Niobium film is patterned using photolithography and alloy etching. To make Josephson junctions, we use E-beam lithography and shadow evaporation of aluminum. The fabricated device is cooled to about 10 millikelvin using dilution refrigerator. This is a picture of our dilution refrigerator, and this is a schematic picture. What looks like silver wire here is a coaxial cables to transmit microwave signal from room temperature to the JPO chips at 10 millikelvin, which are represented by the vertical lines in this figure. Parametric oscillation outputs are amplified by cryogenic low noise amplifiers and also low noise amplifier at room temperature. And then the signal is down converted to radio frequency. And the in phase and quadratic phase of the signal can be obtained from the down converted signals. In order to realize quantum annealing machine based on KPOs, there are several technical challenges. In this presentation, I will focus on 3 topics and explain our activity in the rest of my talk. And the first one is related to precise control of KPOs. Spectroscopic measurements are a useful tool for the evaluation and calibration for precise control. I will describe technique and our technique and the results. And secondly, I will explain about the coupling between KPOs to make their network. I will show preliminary results of 2 and 4 KPOs. And finally, I will focus on the 3-dimensional wiring in order to access the individual KPOs in the integrated structure. We managed to input and read out signals with a 3D structure consisting of interposer and socket. So I will introduce our structure and the result of the demonstration. Now, I will explain the detail about KPO spectroscopy. The reflection coefficient of KPO is measured using a network analyzer. Here is an example of the measurement, which shows the Lorentzian type reflection characteristic around resonance frequency. From this measurement and the result of the power dependence of the reflection properties, we can extract the parameters of KPO as shown in this table. Also, by measuring the flux by dependence of the reflection coefficient, we can see the resonant frequency changes periodically, as shown in this figure. Maybe this is basic one, but a spectroscopy is a useful tool for the calibration of amplitude of signals too. Before I show you the result, I will explain why calibration is important. The optimal schedule for quantum annealing have been studied mainly in spin system, and it can be optimized also for KPO. In our system, the controllable parameters are detuning and parametric drive and coherent drive. Among these parameters, detuning can be determined relatively easily because it's determined by the frequency, by the difference between the frequency of upright signal and the resonance frequency, which can be measured in the previous, can be measured as shown in the previous slide. But the amplitude parametric drive and coherent drive is a little more complicated. As you can easily imagine, the amplitude of drives can be increased if the power of the signal generator is increased. However, the absolute value of the amplitude is not directly determined by that. The amplitude depends on the signal power at KPO located in dilution refrigerator and the coupling strength between the transmission line and KPO. The output from the signal generator is attenuated by KPOs. So to determine the signal amplitude at sample, attenuation and coupling should be determined precisely. If we can determine the amplitude directly, it is the most straightforward method, and spectroscopy allows this. In this method, we measure diffraction coefficient with inducing additional drive to the KPO. When the amplitude of drive is increased, the transition frequency change. The transition frequency can be theoretically calculated with diagonalization of the Hamiltonian. Here, omega nm I represent the transition from state M to N. This is the transition frequency of KPO when the parametric drive is induced. Comparing the calculation result of this transition frequency with the result of KPO reflection measurement, it becomes like this. The curves shown in reflection measurement are theoretically calculation result match very well. It should be emphasized here, attenuation constant is only constant is the only adjustable parameter to compare to data sets. From comparing these two, we can determine the amplitude directly and precisely. We also compare the result with theoretical calculation of reflection coefficient. And reflection coefficient were calculated by this equation. This equation is written as addition of Lorentzian peaks, which correspond to the transition from state M to M. Each peak can be calculated from the transition frequency omega nm, which is determined from the energy and diagonal element of density matrix in steady state. That means population, and they also coupling strength. I show the calculated result of each parameter on right side. And from these values, I calculated the reflection coefficient, and this is the result. The theoretical calculation looks good agreement with experimental results. And next 2 slides, I will discuss a bit more about this result. This graph is the section of this data here. Here, the amplitude of parametric drive beta is 2 pi times 0.21 megahertz. In this small beta regime, the population is concentrated on the state 0. So the dominant peak is the transition from state 0 to 1. This is what I showed as resonance frequency. And in this condition, we choose the frequency of parametric drive is the frequency correspond to the energy difference between state 0 to 2 states without any drive. So the state 0 and state 2 are degenerated. So the peak of omega 1, 0 and omega 1, 2 are overlapped in this condition. On the other hand, when the beta increase and become close to non-linearity chi, here chi is about 17 megahertz, and the energy of state 0 and state 1 becomes close, and the state 2 and state 3 becomes close too. This is a section with beta equals 7.4 megahertz. The omega 1, 2 and omega 1, 0 were degenerated in this. Omega 1, 2 and omega 1, 0 were degenerated in the previous condition, but in this condition, these two they are separated, and both peaks change from the absorption peak to emission peak. This change can be explained well with the population. Let's look at the calculation result of the population. In this calculation, population 1 exceeds the population 0, around beta equal about 1 megahertz. And this links to the change from absorption to emission. And the peaks of omega 2, 1 and omega 3, 0 becomes the dominant peaks in this condition. When the beta is increased, JPO becoming a mixed state of 2. Yes.
Maybe this is the one that's causing the problem. Let's try this one.
Yes.
Thank you. Sorry about this.
Can you hear me?
Yes.
Okay. Thank you.
Sorry about that. Thank you.
どこまで行ったっけ? And okay, I restart, or I forgot what. where I okay, sorry. It takes. And maybe I was talking about 2 dominant peaks in this condition. Okay, thank you. And when the beta is increased, the JPO becomes a mixed state of 2 coherent states. So omega 2, 1 and omega 3, 0 is the transition from these 2 states. And I explained in as I explained in a few slides, a measurement and theoretical calculation matched very well. So I think that the reflection measurement is useful to estimate the population and coupling strength from the results. In the same way as the parametric drive, the amplitude of coherent drive can also be spectroscopically determined. It's like a two-tone spectroscopy. Here are the results. In this case as well, multiple transitions observed in this experiment is very well reproduced by the calculation. When we determine the local magnetic field in the Ising Hamiltonian, determining the photon number is also important, because the actual local magnetic field is determined by the amplitude of coherent drive and the number of photons in the coherent state generated. The number of photons in the KPO can be estimated from the output power from the KPO, but because of the output signal is amplified and attenuated in transmission line, so it is not easy to determine the absolute value of the output power. In our method, the number of photons can be estimated with spectroscopy using ancillary qubit. In this method, ancillary qubit, of which resonance frequency is the same with the oscillation frequency of KPO. When the KPO starts parametric oscillation, output from the KPO can act as coherent drive to the ancillary qubit. So by measuring the reflection coefficient of ancillary qubit, as shown in the previous slide, we can estimate the we can measure the spectral monotriplet, and the distance of these two peaks are determined by 4G alpha. So we can estimate the coupling Z from the spectroscopic measurement, so we can determine the number of photons in KPO only with spectroscopic measurement. Okay, in the next two slides, I will focus on the coupling of KPOs. Here I show the result of two-body coupling of KPOs. When two resonant KPOs are coupled capacitively, the interaction Hamiltonian in rotating flip is written as this. The coupling strength G can be estimated by transmittance measurement as shown here. And the right figure shows the correlation of the Q amplitude of two coupled KPOs. We pumped the KPOs simultaneously and measured the output state of each KPOs. We plotted the histogram of output states as a function of Q amplitude of left and right. And the 4 peaks correspond to the 4 possible oscillating state of KPO. Obviously, a pi 0 and 0 pi state have higher probability than 0, 0 and pi pi state. This means that there is an anti-ferromagnetic correlation between the KPOs. And we also demonstrated annealing operation using 4 KPOs. I will skip the detail, but we managed to observe that there were 4-body correlation, and the distribution probability can be changed by the effect of local field. These results are positive. However, there still remains some open questions, and we are currently working on the additional experiment and theoretical simulations. And finally, I will focus on 3-dimensional structure. The result I have shown so far were obtained using two-dimensional planar device with wire bonding. Up to 4-bit device, there are no problem for two-dimensional wiring. However, increasing the number of qubits make it impossible to wire the central part of the chips two-dimensionally. So we developed 3-dimensional structure as shown here. Here I will show the structure with some pictures. This is an interposer chip and quantum chip containing KPO are flip chip mounted at the center of the interposer. The through silicon beer TSV are formed in the interposer chip, and connect two sides of the interposer. The opposite sides of the interposer probe pin in socket is connected. The probe pins connect to the printed circuit board PCB on the other side. This is a picture of our socket and PCB. This slide shows the data taken with our 3-dimensional structure. We managed to demonstrate spectroscopic measurement and measurement of parametric oscillation output. This is an example of reflection measurement, and multiple measurement at different flux bias gave the flux bias dependence of the resonance frequency. As for parametric oscillation measurement, in phase and quadratic amplitude were measured as shown here. I'd like to stress that although the frequency of parametric drive is about 20 gigahertz, this result shows that the parametric drive successfully transmitted through this 3-dimensional structure. It's still not perfect, but we managed to achieve a 3D implementation with relatively low photon loss state. This is a summary. NEC promoting 2 national projects of superconducting quantum computers. First one is Moonshot project targeting a fault-tolerant quantum computer, and the other is NEDO project targeting a quantum annealing machine. Especially for quantum annealing, we have been developing KPO-based annealing machine and have recently made progress as described here. Here are our collaborators. As I mentioned, this work which I present today is supported by NEDO and Moonshot project. And the device were fabricated in QFAB and NPF in AIST. And this work was done not only by NEC team, but also with AIST team and also Party QC team. Thank you very much for your kind attention. I'd be happy to take any question.